Hello, and welcome to the Gravity Across the Universe worksheet, the extra gravity practice. So to start, we're given 4 different objects. 2 of them we know a mass for, and 2 of them we know a weight for. That weight also being the force due to gravity measured in newtons. Now here it says that Earth's gravitational field strength is 9.8 newtons per kilogram. For the sake of what we've been doing in class, and for nice easy math, we'll go ahead and use 10 newtons per kilogram. Now if you did use 9.8 for the worksheet, that's fine, your numbers will just come out to be slightly different. Now these 4 objects, this is what was done on Earth. So we have object A with a mass of 1 kilogram. Now mass, regardless of where you're at, doesn't change because mass again is the amount of matter that an object contains. So that doesn't change wherever you're at. So everywhere for each one where you see mass A, go ahead and put in 1 kilogram. Everywhere where you see it, 1 kilogram. Should be able to write this out all 4 times. So, object C has a mass of 25 grams. So if we have 25 grams, that means that we can go ahead and change 25 grams into kilograms. And so to do that, we have 25 grams, and there are 1,000 grams for every kilogram, which means that this will equal 0.25 kilograms. So everywhere where you see mass C, you have 0.025 kilograms. 0.25 kilograms. So now these other 2 objects, object B and object D, these were given their weight in newtons. So remember, the force due to gravity equals the mass of an object times the gravitational field strength. And we want to know what the mass is for object B, what the mass is for object D. So we'll go ahead and start with object B, which is 1 newton. That's going to equal the mass times 10 newtons per kilogram. Divide that over. So divide by 10. Divide by 10. We're left with a mass for object B of 0.1 kilograms. So everywhere where you see mass B, 0.1 kilograms. 0.1 kilograms. So that means that for object D, we have a force due to gravity for object D of 12 newtons. So 12 newtons equals the mass times 10 newtons per kilogram divided by 10. Have a mass for object D of 1.2 kilograms. 1.2 kilograms. So again, everywhere we see mass D, 1.2 kilograms. 1.2 kilograms. So now we have all the masses sorted out. And now we want to be able to find the force due to gravity on each object. So we'll start with Saturn. Saturn says that the force due to gravity on object A is 9.1 newtons and the mass of the object is 1 kilogram. So that means that if we use force due to gravity equals your mass times the gravitational field strength, and we're going to use this equation the rest of the homework set. Right now we have the force due to gravity is 9.1 newtons, and we have the mass of the object is 1 kilogram. So we're trying to find what the gravitational field strength is in this case. We're trying to find G. So we can put in 9.10 newtons equals 1 kilogram times G. Divide 1 kilogram over, and we get 9.1 newtons per kilogram for G. So 9.1 newtons per kilogram. So now for the rest of this one, since we know what the gravitational field strength is and we know the masses, you plug your mass. So we have mass B, mass C, and mass D. If we multiply mass A by the gravitational field strength, we get 0.91 newtons. Multiply mass C by the gravitational field strength, so we take 0.025 kilograms, multiply that by 9.1 newtons per kilogram, we get 0.2275 newtons. And same thing for mass D, 1.2 kilograms times 9.1 newtons per kilogram. We will get 10.92 newtons. So now we'll bump on down here to Rigel 4. And again, we're given that same starting point where we have a force due to gravity and a mass. So again, we will start with that F, that force due to gravity. And actually, that would be 25 newtons. And 25 newtons equals 1 kilogram times G. Divide the 1 kilogram over, and we get a G, a gravitational field strength, 25 newtons per kilogram. 25 newtons per kilogram. And again, using that nice basic equation, because now we're trying to find the force due to gravity on each object, equaling its mass times the gravitational field strength. Gravitational field strength here. And then we have the three masses that we can plug in for M. So when we do this, we get 0.1 kilograms times 25 newtons per kilogram. We get 2.5 newtons. The force due to gravity on object C, so we take 25 newtons per kilogram, multiply that by 0.025 kilograms, and we get 0.625 newtons. And for D, we get 1.2 kilograms times 25 newtons per kilogram for a force of 30 newtons. So moving on to the third part, onto algin. I believe that's how it's pronounced. For this one, we already know G as 4 newtons per kilogram, and we know all the masses. So that means that we know that the force due to gravity is equal to the mass times the gravitational field strength. We are given the masses and that gravitational field strength. So when we multiply 1 kilogram by 4 newtons per kilogram, we get a force of 4 newtons. Multiply 0.1 kilograms by 4 newtons per kilogram, we get 0.4 newtons. For object C, 0.025 kilograms times 4 newtons per kilogram, and we get 0.1 newtons for the force of that object, for the weight of that object. And for object D, we have 1.2 kilograms times 4 newtons per kilogram to get 4.8 newtons. And the last one, to con 5, we're given a force due to gravity on object D of 48 newtons. So again, we have 48 newtons equals the mass, 1.2 kilograms, times the gravitational field strength on the planet. So we divide by 1.2 kilograms, so we get a G of 40 newtons per kilogram, which is 10 times what it is here on Earth. So then using our trusty force due to gravity equals the mass of an object times the gravitational field strength. Now that we have that gravitational field strength, we can multiply masses A, B, and C by that number to find the force due to gravity on each of them, to find the weight. So for mass A, 1 kilogram, multiply that by 40 newtons per kilogram, and we will get 40 newtons. For mass B, 0.1 kilogram, we'll multiply that by the same 40 newtons per kilogram, and we will get 4 newtons. And the last one, we have 0.025 kilograms, multiply that by 40 newtons per kilogram, and we will get 1 newton. That is the Gravity Across the Universe practice sheet.